conic bundle on conic bundles with canonical singularities. Yeah, please.
Okay, so thanks a lot for the invitation. So today I will talk on Shelford's conjecture on conic bundles with canonical singularities. So this is a joint work with Chen Jiang and Yujie Luo. So first, I would like to mention that we work over the complex numbers. And so there's a conjecture, which we call the minimum model conjecture in bidimensional geometry. So it predicts that for any projecting normal variety, so which is bidimensional to a minimum model or a modifiable space. So roughly speaking, so a minimum model is a projective normal variety X with Kx is nav, and a modifiable space is a fibration. So from X to Z, such that minus Kx is ample over the base Z. And the conjecture is known in dimension 3. And so I would like to mention that even if we start with a smooth variety, it might end up with a singular one. So we need to introduce some definitions of the singularities, or I would like to recall you the definition of singularities. So let X be a normal variety such that Kx is Q Cartier, or I can assume that X is a Q Grunstein variety. I let F to be a resolution, and I can write Ky to be the pullback of Kx plus the sum of Ai, Ei. And then we can define the so-called the minimal log frequency of this variety X. So it is equal to the infimum of Ai plus 1. So for any such kind of F and any such kind of Ei. And we call X is terminal if the minimal log frequency is larger than 1. And we call it is canonical if the minimal log frequency of X is larger than or equal to 1. And it is epsilon log KLT. So if the minimal log frequency is larger than, strictly larger than epsilon. And if it is epsilon log canonical, then the minimal log frequency is larger than or equal to epsilon. So these singularities appears naturally in the study of bidimensional geometry. And from the definition, we can see that the larger the MLD is, then the better the singularities are. So for example, if the MLD is equal to the dimension of X, then then it is expected that the at such kind of point, so the center of such kind of point, it is smooth. Or if we can show the MLD of the variety is larger than n, then it is expected that of close point of this variety are smooth. So for example, in dimension, the definition of the terminal, it is equivalent to the smooth. And the definition of the canonical is equivalent to the Dulac singularity. And moreover, so if we have a cyclic quotient singularity of type 1 over n, 1, then the MLD is equal to 2 over n. So here is a natural question. So for given a modifiable space from X to Z, then can we control the singularities of Z? So by those of X. So this means that, so for example, X has terminal singularity, then can we control the singularity of Z? Or X has some better singularity, such kind of epsilon log canonical singularities, then could we control the singularity of Z? So there's a related question, or as a special case of this question, so which is called the Iskowski conjecture. And later it was proved by Murray and Prokop in 2008. So the Iskowski conjecture is about a Q-conic bundle, and it predicts that the singularity of Z could be controlled by the variety X. So let's first introduce the definition of the Q-conic bundle. So a Q-conic bundle is a proper morphism from X to Z. such that X is a terminal threefold and Z is a normal surface. And all fibers are connected, and the dimension of all the fibers is equal to 1. So this means that there's no other fibers of high dimension. So all the fibers is equal to 1. And the dimension is equal to 1, and minus kx is ample over Z. So such kind of Q-canonical bundles appears in the modifiable space in the minimal model program. And so that Iskowitz predicts that the base Z of any Q-canonical bundle has only Duval singularity. And moreover, he expected that the singularity is only of type A. So this means that it could not be of type D in the classification of Duval singularities for surfaces. So this is the content of Iskowitz conjecture. So this conjecture has some applications to the rationality problem of Q-canonical bundles, and this might be the motivation of Iskowitz to ask such kind of conjecture. And indeed, in Murray and Prokof's proof, so they gave a complete local classification of Q-canonical bundles. So this means that So this means that they not only prove the Iskowitz conjecture, so which means that they show the base Z has only Duval singularities of type A, but they also give some local equations to classify all such kind of singular bases. So their results, in some sense, are much stronger than Iskowitz predicts. And so there's a natural question. So how about singularity of Z if we relax the singularity assumption of X from terminal to canonical? So recall that in Iskowitz conjecture, so we require that the singularities of X to be a terminal variety. So here the question is that how about singularity of Z if we only assume that X is canonical? So this means that we allow the MLD of X is equal to 1. And later, Shortworth he conjectured that in this case, they is no longer to be canonical or no longer to have Duval singularities. So there's a gap. He conjectured that in this case, there is a 1/2 log canonical. So canonical, in some sense, so it is equivalent to say that Z is of 1 log canonical. So if you recall the definition of the MLD, so by canonical we mean that MLD is larger than or equal to 1, and 1/2 log canonical means that the MLD is larger than or equal to 1/2. So there's a gap. Just or if we only relax the condition that X is terminal to X is canonical. So there will be a gap on the singularity of the base. And this example indicates that 1/2 is optimal. So this example is actually it is shown in Prokof's paper, but we need some modification. So in our paper we also give this example. So the example is that if we consider the action Z4M on this space P1 times C2, so the action is given by we send XUV to minus X CU C to 2M minus 1's power V, where C is a primitive 4M's root of units. And if I let my X to be the quotient of P1 times C2 and this action, and I let Z to be the C2 quotient by Z4M. So if we restrict only to UV chart, so we can define Z and pi to be the natural projection. So in this case, we can show that X has only canonical singularities along the fiber over the point O. and Z has an isolated cyclic quotient of type 1/4n, 4n minus 1. So at the origin point O. And moreover, the MLD is equal to 1/2. So in order to show MLD is equal to 1/2, maybe we need to use some results from toric geometry. So by Amorous results, we can show that the MLD is equal to 1/2. And so from this example, you can see that if X only assumed to be canonical, then it is possible that the MLD of Z is equal to 1/2. And now I would like to introduce our first main results in today's talk. So the theorem A, so this is my joint work with Chen Jiang and Yujie Luo this year. So for a contraction from X to Z, so I let pi to be a contraction from X to Z, so between normal varieties, and if the relative dimension or the dimension of X minus the dimension of Z equal to 1, and X has canonical singularities, and Kz, so Z is a Q-Grun's type. So this means that Kz is Q Cartier. And if we assume that minus Kx is ample over Z, so just like in the setting of Iskop's conjecture, then the base of singularity is always of 1/2 log canonical. So as I mentioned earlier, by the previous example, the value 1/2 is optimal. And so I would like to remark that if X is terminal and all fibers of pi are of dimension 1, so just like in the setting of Iskop's conjecture, so in the Iskop's conjecture can require that the fiber is equal to, the dimension of the fiber is equal to 1. So here in our theorem A, so there's no assumption on the fibers of pi. So if we additionally assume that all the fibers of pi are one-dimensional, then we can, that example shows that the value then we can show that Z is 1/2 KLT. So this means that the MLD could not be equal to 1/2, and there's examples indicates that this value is optimal. So if the dimension of X is larger than or equal to 4, so the Iskop's conjecture is about the dimension of X is equal to 3, and our result is about high dimension. So in this case, in the same setting, we can see that in high dimensional case, the singularity of the base is 1/2 KLT. So it is no longer be canonical again. And so for the proof of theorem A, so we use pairs and the so-called canonical bundle formula. So canonical bundle formula plays an important role in our proof. And in order to show to use canonical bundle formula, so it is very natural to introduce the pairs in the proof of this theorem, because we need to construct a relative travel pair, and we need to apply the canonical bundle formula. So here for the condition minus Kx is ample over Z, then we can construct a relative travel pair and does not increases the singularity of X. And indeed, we will see later that we can relate this condition to, for example, we can only assume that minus Kx to be bigger than n over Z. So first, I would like to introduce the relative pairs. So it is similar to the pairs in bidirectional geometry, but it also has some differences. So for a relative pair, so it consists of normal varieties X and Z, and also a contraction from X to Z, and also a point Z on my variety Z. And B is an R divisor, so effective R divisor, such that Kx plus B is R Cartier. And moreover, we require that this point Z, the dimension of Z is less than the dimension of X. So the reason is that we would like to consider all the prime divisors E over my small point z. And if the dimension of small z is equal to the dimension of x, then there's no such kind of prime divisors. Because, for example, I let x to z to be an identity map, then z is a generic point of x, then there's no such kind of prime divisors, so which is over the generic point of x. And so if pi is identity map, then we may write x z b instead of x z small z b. And then we can define again the so-called log discrepancy of xb. So let y to x be a proper binomial morphism, and let E be a prime divisor on y, then we can define the log discrepancy of E with respect to the pair xb. So it is the same definition as the definition of the log discrepancy in usual pairs. So it is equal to ky minus the pullback of kx plus b. I compute the multiplicity plus 1. Then I can define the MLD of a relative pair. So here, the MLD of this relative pair is equal to the minimum of AEXB. So here I only interested in such kind of E such that the center of E is equal to the closure of Z. So this is not the same as the definition of MLD of X in the beginning of our talk. So in the beginning of our talk, there's no assumption on the center of Z, and here we need that the center of Z is exactly equal to the closure of this point small z, and we can show that the minimum could be achieved. So then this definition is well defined. So it takes value from the minus infinity and the union of the negative real numbers. So this number measures singularities of xb in a neighborhood of z. Yeah. So although we require that the center of z is equal to the closure of z, but this number measures singularities of xb in a neighborhood of this small point z. And we say that the relative pair is log canonical if, again, the MLD is larger than or equal to 0. So then I would like to define the log canonical thresholds. So it also appears in the definition of the canonical bundle formula. So I let my xb to be an log canonical pair and D be an effective R-Cartier R divisor. Then the log canonical threshold of D with respect to this relative pair is equal to the largest number T, such that xb plus TD is log canonical. So again, this is similar to the usual definition of the log canonical thresholds. But so the difference is that I require the singularity. So it is log canonical. So it is about this relative pair. And then we can introduce the canonical bundle formula. So some key results was proved by Kamata and Amro. So if I let xb be an log canonical pair and pi to x to be a conjecture, such that kx plus z is R linearly equivalent to z over z to 0 over z, and kx plus b is R linearly equivalent to the pullback of L for some R-Cartier R divisor. So then we can show this. And moreover, so we have the so-called canonical bundle formula. So we can write kx plus b to be R linearly equivalent to the pullback of kz plus bz plus mz. So for some divisor bz and mz on my base variety z. So where bz is the so-called discriminant part of this canonical bundle formula. So it could be computed by the log canonical thresholds. So it is for each point, so of conjunction 1 point p on my z, then the corresponding coefficients it equal to 1 minus the log Canova threshold. And then we can define the module part. So the discriminant part only depends on the log Canova threshold of this pair. And the module part, actually, it depends on the choice of air. So because, so for different choices of air, then the module part might be different. So it is equal to the air minus kz minus mz. So this is about the canonical bundle formula. And so the advantage of introduce the canonical bundle formula is that, so for example, XB is log canonical, then we make sure that the singularity of Z, BZ plus MZ is also log canonical. If we regard Z, BZ plus MZ as a generalized pair, and also by a conjecture of Shelford and Prokop, the so-called B semi-emptiness conjecture, they predict that the module part MZ is so-called B semi-emptiness. So this means that on some high model of Z, and we can also define MZ. Then in some high model, MZ is semi-ample. So this means that MZ will not make the singularities of Z, BZ bad. So the singularity of XB will control the singularity of Z, BZ. So and then we can apply some induction to finish the proof of some theorems in bidimensional geometry. And now it's time to introduce the Shelford's conjecture. So Shelford he conjectures that for the such kind of canonical bundle formula setting, so if X is of final type over Z, then if we can control the singularities on X, then we can control the singularity on Z for any relative travel pairs. So if XB to be a pair and the codimension of my small point Z is larger than or equal to 1, and the relative dimension of X2Z is, I fix the relative dimension, so it is equal to D, and the MLD of this relative pair is larger than or equal to epsilon. And I require that this pair is a relative travel over my base, and moreover, I require that X is of final type over Z. So this is very crucial. The assumption that X is of final type over Z. Then Shelford predicts that we can choose MZ so that the MLD of this pair Z, BZ plus MZ is larger than or equal to delta. So if I can choose MZ to be an effective divisor, then Z, BZ plus MZ is a usual pair. So it is not a so-called generalized pairs. And then we can talk about the MLD for the usual pairs, and he predicts that in this case, the MLD is larger than or equal to delta. So we can control the singularities of the pair. So not only control the singularities of the base Z, but the pair induced by the canonical bundle formula. So here our formulation of this conjecture. So it is slightly stronger than the formulation of Shelford's conjecture in the previous lecture. In previous lecture, so people usually, so for example, in Bierka's paper, so he is only interested in the usual pair setting. So it is not about the relative pair. So for example, so here the assumption on the MLD of this relative pair is replaced by the usual pair. But there are some differences. And for the relative pair, the assumption actually is weaker, because we already require that all the prime divisors over this small points, the MLD is larger than epsilon. So this assumption is weaker than the usual assumption that MLD of XB is larger than epsilon. So a strong assumption. So if MLD XB is larger than or equal to epsilon, then in Bierka's paper, he proved this conjecture. So in several cases, so one case is that if the general fiber F and I restrict B to the general fiber, so it belongs to a bounded family. So where F is the general fiber. And yeah, so by bounded family, so since it is of final type and the singularity is of epsilon log canonical, then actually you by the BAB conjecture or BBAB theorem, you can show that F belongs to a bounded family. But here can require that FB restrict to F, so it belongs to a log bounded family. So in general, we could not show that so FBF so belongs to a log bounded family because the coefficients of B, so there's no lower bound. So if there's lower bound for the coefficient of B, then FB restrict to F. So this pair belongs to a bounded family just by the BAB conjecture. And that's another case is that the dimension of X is equal to the dimension of Z plus 1. So this means that the relative dimension is equal to 1. Then Bierka proved the theorem under these two cases and a stronger assumption. And so there's two more remarks. So the first remark is that the Shorthouse conjecture might be a consequence of another conjecture of Shorthouse. So the so-called Shorthouse epsilon log canonical commutative conjecture. So the statement of Shorthouse epsilon log canonical commutative conjecture, you can find the statement maybe in Bierka's PhD thesis or in my joint work with Guodu Chen this year. And so in following Bierka's idea, so we prove that so this conjecture holds when the dimension of X equal to the dimension of Z plus 1. So we follow the Bierka's idea and also follows our main results in this paper. So where we prove the Shorthouse epsilon log canonical commutative conjecture for the relative pair. And so if the relative dimension is larger than 1, it is also expected, and indeed we prove maybe a weak version of Shorthouse conjecture by assuming Shorthouse epsilon log canonical commutative conjecture. And also Shorthouse conjecture implies a conjecture of McKernan, which on modifiable space, so without the boundary. So if I let the boundary equal be equal to 0, and I assume that minus kx is ample over Z, and maybe the Picard number, the relative Picard number is equal to 1, then McKernan predicts that if X, the singularity of X is epsilon log canonical, then the singularity of Z is of delta log canonical. So it could be shown easily that McKernan's conjecture follows from Shorthouse conjecture. And so in our work, so or in Shorthouse conjecture on conical bundles, so we want to know exactly the optimal value of delta. Or in general, we would like to know the optimal value of delta d epsilon. So delta depends on the dimension of the relative dimension and the singularities on X. And so in our work, so or in today's talk, we are interested in the special case when the relative dimension, the relative dimension is equal to 1, and when epsilon is larger than or equal to 1. So because we assume that the pair is canonical, so this means that MLD is larger than or equal to 1. So we are interested in a case that epsilon is larger than or equal to 1. Then in our joint work, we give the optimal value of delta 1 epsilon. So the optimal value is equal to epsilon minus 1/2. So in particular, in Shorthouse conjecture on conical bundles, if we take epsilon to be 1, then we get that the singularity of the base is equal to 1/2. So this gives us the positive answer to Shorthouse conjecture. So now I would like to state our second main theorem. So it is about a pair version of Shaw's conjecture on conic bundles. So again, I let XB be a relative pair, and the dimension of Z so is larger than or equal to 1. And if we assume that the relative dimension is equal to 1, the MLD is larger than or equal to 1, the pair is relative travel, and the generic fiber is a rational curve. So somehow, so this is equivalent to assume that X is of final type over Z, because in dimension 1 case, so a rational curve, so it is equal to so if it is smooth, then it is P1, then it is of final type. So the general fiber is of final type. Then we show that we can choose the module part to be an effective divisor, so that the MLD of this pair is larger than the MLD. So we can forget about the module part. It is larger than the MLD of the pair XB minus 1/2. So on X, and it is larger than or equal to 1/2. So if I let that the MLD of this relative pair equal to epsilon, then this means that our theorem shows that the singularity on the base Z BZ plus MZ, the MLD of this pair is larger than or equal to epsilon minus 1/2. So if we let MLD equal to epsilon, so this means that the value of delta we may take to be epsilon minus 1/2, and also there's examples indicates that this value is optimal. And so indeed, if you are familiar with canonical bounding formula, then in some cases, maybe people are interested in a more general setting. So which means that so we do not require XB be a pair. So this means that we do not require B to be an effective divisor, but we need to assume that B is effective on respect to the general fiber, and under some technical assumptions, so the called LC travel fibration for such kind of XB over Z, then we also show that the theorem holds in this setting, yeah, for the so-called LC travel fibration. And so another remark is that the lower bound on MLD, so it is optimal. So there's example shows that this value is optimal. And so as a corollary of our main theorem, we show this corollary. So almost in the same setting, but we replace the singularity assumption on the relative pair by XB to be canonical, and B has no vertical irreducible component over Z. So we replace MLD of the relative pair is larger than or equal to 1 by this weak assumption somehow. Because for the a stronger assumption, because for this assumption, we can show that the MLD of the relative pair is larger than or equal to 1. Because XB is canonical, so for any external divisor over X, its log excludency is larger than or equal to 1. And for any prime divisor on X, since B has no vertical irreducible component over Z, so this implies that MLD of any prime divisor on X with respect to this relative travel pair. So if we adopt the notation in our previous slide, then the MLD is larger than or equal to 1. So for the local setting, so you can see that this assumption is weaker than is stronger than the assumption on the relative pair setting. But here we are interested in the global singularity. So here we can show that we can choose MZ, which is larger than or equal to Z, so which is effective, such that this pair is a 1/2 log canonical. So the result is also slightly stronger, because we show that the whole pair, so the singularity is a 1/2 log canonical. So it is not only about the singularities over the given point Z, yeah, but also under the stronger assumption. And we can show that actually for this result, it follows from our previous theorem. And now I would like to show that why theorem A is a direct consequence of our corollary. So recall that in theorem A, the assumption is that the relative dimension is equal to 1, and x is canonical, and minus kx is ample over z. And what we need to show that is that the singularity of z is 1/2 log canonical. And so we wish to apply this corollary. So since minus kx is ample over z, so we can show that there exists, we can take a general divisor b, which is effective, such that b is q linearly equivalent to minus kx over z, and xb is canonical. So it will not make the singularity better, worse. And so moreover, we can show that xb satisfy the assumption 2 and 3 in our corollary. So this means that xb is not only canonical, but also that b has no vertical irreducible component over z. So this is because we can choose a general b. So in this q linear system, so we can assume that b has no vertical irreducible component over z. And since by the choice by the construction of b, we see that kx plus b is q linearly trivial over z0. And moreover, since the relative dimension is equal to 1 and minus kx is ample over z, then we can show that x is of final type over z. This also follows from that. It also follows from that xb. So indeed it is QLT and b is big over z. So x is of final type over z. You can also see from the construction of xb. And then by our corollary, we show that this pair, so which is induced by the canonical Boundary formula, so it is a 1/2 log canonical. So in particular, so the singularity of z is of 1/2 log canonical. So this finishes the proof of the Shelf's conjecture, or the theorem A. So which only so the statement is about the singularities of z. So you can see that. So why it is natural to introduce pairs to consider, although the Shelf's conjecture is only about the singularity of x and z. So because it is very natural to apply the canonical Boundary formula. Okay, so this is about the theorem A. And so then the next question is about how to prove our theorem B, so about the relative pair. So about this relative pair. So this is the next question. And so before I introduce the proof of idea of our theorem B, I would like to give a comparison of our theorem with Murray-Perkoff's results. So in the setting of Shelf's conjecture, so our result is about if we fix the relative dimension. So we recall that the dimension of x minus the dimension of z is equal to 1, and the singularity of x is terminal, and minus kx is ample over z, and all fibers are of one-dimensional. So indeed we prove in a weaker assumption that we assume that x is of final type over z. But here we relax the assumption. We require that minus kx is ample over z. So in order to fit with the setting of Shelf's conjecture. So then our result implies that z, the base z, is of 1/2 KLT. So the singularity is 1/2 KLT. And Murray and Perkoff's results, so they only prove the case when the dimension of x is equal to 3 and the dimension of z equal to 2. So their result gives no information when the dimension of x is larger than or equal to 4. And the rest of 3 conditions there are the same. So x is terminal, minus kx is ample over z, and all fibers are of dimension 1. Then they show that z is of dual singularity and of type A. So this means that, indeed, if we apply the ACC of MLD for surfaces, so the Duval similarity means that the MLD is larger than or equal to 1, but since the MLD satisfies the ascending chain condition, so we can show that there's no values of MLD between 2/3 and 1. So this means that we can replace the conclusion that the MLD is larger than or equal to 1 by the MLD is larger than 2/3. So this means that they show that the singularity of Z is of 2/3 KLT. And so you can see that there's some gap between 1/2 and 2/3. But I also would like to remark that, so in dimension 2, the MLD, the largest accumulating point of MLD in dimension 2 is 1/2. So although there's a gap between 1/2 and 2/3, but indeed we can show that there's only finitely many values between this open interval. So between 1/2 and 2/3. This is because although 1/2 is an accumulating point, but by the ACC property, maybe by the ACC property, there's some values which is there are maybe some infinite many values which is larger than 1/2, but if we can show that the singularity is better than 1/2 plus epsilon, then there's only finite many values between this open interval. And so what I would like to emphasize is that our result is more general and optimal in the case when the dimension of X is larger than or equal to 4. Because in this case, this means that this example shows that the singularities of Z is of 1/2 KLT. So this means that we could not improve the singularities of Z. So in high dimensional case, but in lower dimensional case, we know by Iskov conjecture or Mori-Prokof's results, we know that the singularity could be improved to 2/3 KLT. So it might be an interesting question that whether we can recover Mori-Prokof's result. So only about Z Duval singularity by our results. So this is a remark and also a question. And so now I would like to introduce the proof of theorem B. So by a result of Prokop and Shortfall, so where they show that MZ, actually they show that it is B semi-ampleness. So this means that on some high model of Z, we can show that MZ prime is semi-ample. Then by their results, and if we only need to control the coefficients of MZ from above. Also, maybe we need to control the coefficients of BZ on some high model. Yeah, and then we can cut in Z by high plane sections, and we may reduce the problem to the surface case because the coefficient of BZ, the behavior, its behavior is good under the cutting of high plane sections. And so now, in order to show theorem B, we only it suffices to show theorem C. So if we are cutting Z by high plane sections, or if so you are only interested in the surface case, so we can assume that the dimension of X minus the dimension of X is equal to 2, and in this case, the dimension of Z is equal to 1, and the MLD is larger than or equal to 1, and the generic fiber is equal to P1, so it is rational curves, and B is effective on F. And so here, in order to show Shortfall's conjecture or to show theorem B, so we need to prove it in a slightly larger class of pairs. So here I don't require that B to be effective. So B is not necessary to be effective. So the reason is that in our proof, So in order to control the singularities, we need to take some high model of Z, and we need to take the pullback. And then in this case, the pullback of XB to some high model may not be a pair. So the pullback of B may not be effective. So we need to prove the theorem in surface case for pairs, subpairs. So to simplify the dimension reduction. And in order, if we are only interested in to prove Schoffel's conjecture, then we could there are some reduction that it suffices to prove the surface case for usual pairs, but the reduction may be much more complicated because in the process we need to keep the pair to the XB to be a pair. And so then by some MMP arguments, so indeed, although here in our theorem C, so we only we assume that XB to B is not necessarily effective, and X may have some singularities. But since here we are under the surface setting, so we may take a minimal resolution, and we may run some MMP to contract the negative part of my divisor B, and finally we may reach a more verifiable space. So during MMP we can show that X is smooth. So by some MMP arguments, we may assume that B is effective and X is smooth, and also X over Z is a P1 bundle, and the minimal lattice frequency is equal to 1. So,
hello, Jinju.
Hi.
In the statement C, the last line, you have a semicolon pi star Z. So pi star Z is divided as a other boundary.
So sorry, I can't.
The last line. Pi star Z.
Yeah. So pi star Z. So in this case, so here yeah, pi is the morphism from X to Z, and since here the dimension of X is equal to 2 and the dimension of Z is equal to 1, so Z is a close point. So we may take the pullback of this close point.
So what's the meaning of this notation? Semicolon.
So you mean the pullback of pi star Z? So
no,
it is a divisor
of LCT.
So LCT means the log canonical threshold.
Yeah, this I know. So you have a pair B the boundary. So then you have after B you add one more. What's this meaning? Meaning you look at the center containing this one.
Yeah. So the meaning is that so I consider X B plus T times pi star Z. And then I can consider all the possible
I see. Okay.
time divisors E such that the center of E is equal to Z. And I require that the
I see, like
equal to
like in Ambrose notation, right? You multiply this 5 by T, okay? Like in Ambrose.
Yeah. So the difference
along this
is that so we are interested in the relative pair. So I only care about all the centers E such that the center of E on Z is the close point Z.
Okay, thanks. Yeah.
And then we can show that the log canonical threshold is larger than the MLD minus 1 over 2, and is larger than 1/2. So then by theorem C, so if theorem C holds, then we can show that the MLD of the base indeed the coefficient we can control the coefficients because by the canonical bundle formula, so the coefficients of BZ is defined by the log canonical 1 minus the log canonical threshold. Yeah. And so then by some MMP arguments, so we may reduce to a case that B is effective and X is smooth, and XZ is a P1 bundle, and the MLD of this relative pair is equal to 1. And indeed, if we are only interested in Shelford's conjecture, indeed, indeed we may assume that the MLD is equal to 1. But since in theorem B we consider a more general setting, so that's when we need to introduce some reduction to reduce to the case that MLD is equal to 1 and B is effective. And so now we have the following statement. So this is a simple version of theorem C. So I let X be to be a pair. So here B is effective, Z is a close point, and X2Z is a P1 bundle surface. So the dimension of X is equal to 2, and XB is a relative travel pair. MLD, the MLD of XB is equal to 1. And F, I let F to be the fiber over Z. Then in order to show the theorem, we only need to show that the log canal threshold of this relative pair with respect to F, so it is larger than or equal to 1/2. And so here again, so the value 1/2 is optimal. The reason is that, for example, we can take X to be P1 times Z. So, and then B is a 2-2-1 multisection. So just like a conic. So B is a conic, and I take my fiber F to be tangent to B. And then in this case, we can show that the log canal threshold of XZ B with respect to F, so it is larger, it is equal to 1/2. So the reason is that so indeed you can prove it by just by a blob. So if you have a conic and you have a line which is tangent to this conic, then if you take one blob, then you can compute the MLD of this pair, and you can show that the optimal value to let XB plus TF to be log canonical is that T is equal to 1/2. So this means that XB plus 1/2 F is log canonical, and you could not increase the coefficients of F. And in order to show this simplified version of theorem C, so we prove this theorem in a local version. So because the log canal threshold, so for this value, so we are interested, we're only interested in all the prime divisors E over -1 point Z. So in order to show the log canal threshold, we can consider, we can focus on all the close points on my fiber F, because only, so if for a prime divisor, so if the center of this prime divisor on the base Z is equal to small z, then the center of this prime divisor must lie on X must lie in the fiber of F. So we in order to show the log canal threshold of this pair, so the relative pair, so we only need to consider all the close points on my fiber F, and to show that this pair is log canonical. So I mean XB plus 1/2 F, so it is log canonical on each close point of this fiber F. So we are able to reduce the theorem C to the following local statements. So I let XB be a germ of a surface pair. So this means that there's a usual pair XB, and I have a close point P on X, so such that X is smooth, because in our simplified version of theorem C, So we reduce to a case that X is smooth. The ambient variety X is smooth. And so here the divisor C plays the role of the fiber F in the simplified version. So I let C to be F, and since by the assumption that the MLD of the red pair is equal to 1, I know that B does not contain the component of F. Because if B contains the component of F, then I just take the prime divisor F to E to be F. Then the MLD is less than 1, because B has some the coefficient B contains the component of F. So this means that B could not contain the F. So it translates to this assumption that F does not belong to the support of B. Yeah, so C does not belong to the support of B, and so here in this assumption we may reduce to the case that F is smooth. So this means that C is a smooth curve at P, so near P, and moreover, so we can translate the MLD assumption. So this assumption, so this partially explains why we could not show the result for the case when the MLD is less than 1. So the reason is that in surface case, when MLD is larger than or equal to 1, then we can translate this assumption to the assumption on the multiplicity. So to let MLD is larger than or equal to 1, it is equivalent to that the multiplicity of B at this point is less than or equal to 1. So when the MLD is less than 1, then there's no equivalent definition or the equivalent statements. And so here I also need to let X plus B is linearly travel over the base. So since I know that F is P1, so this means that the degree of B restricted to F is less than or equal to 2. So we can also translate it to the local setting. This means that the local intersection of B with C, so at the point P is less than or equal to 2. And then in this case, it suffices to show that the log Carnot threshold of this relative pair XB with respect to C is larger than or equal to 1/2. Because if we can show all the close point P on the fiber of F, so satisfy this inequality, then so the inequality holds for this relative pair XB F. Yeah. So it suffices to show the simplified version of theorem C in this local setting. And so this is our last step to show this local setting. Yeah. So indeed, we show a more general statement. So we show that if the multiplicity of B so is equal to M, so which is less than 1, and if we fix the local intersection to be I, so there's no assumption on I to be less than or equal to 2. So this is a more general setting, and we can show the log Carnot threshold. It is larger than or equal to the minimum of 1 plus M over I minus M. And so in particular, if I let I equal to I to be less than or equal to 2, then in this case, I can, so following from this inequality, I see that the log Carnot threshold is larger than or equal to 1 minus M over 2, so which is larger than equal to 1 over 2, so 1/2. So you can see that theorem D is a generalization of theorem C. And so also there's examples indicates that the values in theorem D is optimal. So for example, we can let B to be x to P's power plus y to Q's power for some lambda, so which is less than or equal to 1 over P, and C is locally defined by x equal to 0. And then we can compute the multiplicity of B at the point P, which is equal to lambda P, because P is less than or equal to Q. And So by the constraint of lambda, so we know that lambda p is less than or equal to 1, and the local intersection, so it is equal to lambda q, because I let x equal to 0, and then I can see that the local intersection is equal to lambda q. Then in this case, we can show that the log Cantor threshold is equal to the minimum of 1 and 1 plus p over q minus lambda p. So again, in order to show log Cantor threshold, in this case, you might take some blow up, then you can compute the log Cantor threshold. And so finally, we only need to show the CMD for this local setting, and we give 3 different proofs of this theorem in our paper. So the first proof is by Quartas method and by the convexity of the log Cantor thresholds. So this means that we use the convexity of the log Cantor threshold, and we work in the analytic setting, and we reduce to a case that B is irreducible. So for this reduction, this reduction is crucial in our proof. And for this reduction, we only need to use the log Cantor, the convexity of log Cantor threshold, but by a carefully choosing of such kind of divisors. And then we may use Quartas result to compute the log Cantor threshold in the analytically irreducible setting. So this is the first proof. And the second proof is that we use Verchenko's method and some curving trick. But for this method, we cannot prove this general version of the theorem. So Verchenko's method could be applied to compute the set of log Cantor thresholds for surface in a surface case. So for this case, we are unable to prove this this general setting, but it could be applied to prove the continuity of shock force. So which means that the multiplicity is less than or equal to 1, and the local intersection is less than or equal to 2. And the last proof is based on the Newton polygon and the convexity. And for this proof, also we can prove the theorem D in full generality. So in this form. So in our paper we provide 3 different proofs of this theorem. So I think I stop here, and thank you for your listening.
Okay, thank you. Yeah, thanks to Jinju for the nice talk. So any questions or comments?
So what is the result of Shawcross and Pockcross that you mentioned and you used in this proof?
So we use the result of Pockcross and Shawcross on the B semi-ampleness conjecture. So this means that in the canonical Bernoulli formula, so they show that on some high model Z prime of Z, they show that the module part MZ prime, so which is also induced by the canonical Bernoulli formula. So on the high model MZ prime, so it is semi-ample. So this means that if we take the some high model of Z, then since MZ prime is semi-ample, so it will not made our singularities worse. So in order to show theorem B, so it suffices to control the coefficients of BZ. Because so if the coefficient, so because the singularity is bad, then this means that there's some prime divisor E such that the log frequency is small. Then on some high model we may extract this prime divisors. And since MZ prime, so it is semi-ample. So this means that if the singularity is bad, then this means that the coefficient of BZ prime is very large. And so in order to show this conjecture, we only need to control the coefficient of BZ indeed on any high model of Z in the canonical Bernoulli formula.
So what is the setting of their theorem? Also relative dimension 1 or more general?
Yeah, they always show the case the relative dimension is equal to 1, and but the case that the relative dimension is larger than or equal to 2, I think it is still open. So okay. This is a very difficult conjecture, I think.
Okay, thank you.
One technical question. So you consider this pair or generalized pair. In the generalized pair case, you have the left part. So if the left part, you regard the left part as a part of the boundary, or or just regard the left part as left part. So then you have two different calculation of how do you call the frequency? Which one is bigger? You can regard the left part as part of the boundary, or just as
So
are they the same?
You mean there are two? So you mean the singularities of z bz and the singularity of z bz plus mz?
Yes. If m is regarded as a left part, or if m happen to be effective regarded as part of the boundary, then you have two different frequency. Which one are they the same or different?
Yeah. So in general, so by the negativity lemma, you can show that the singularity of the z bz is no worse than the singularity of z bz plus mz. So you can show it by the.
No, my question is that you regard m as a part of the boundary, or regard as generalized pair.
Oh, in this case, yeah. In this case, I'm not sure. So maybe there's no way to compare the similarity. So it depends on the choice of MZ.
I see that.
So if you so the MZ, if you choose to be a good divisor, then it will not. So for example, MZ, if you choose to be semi-ample, then
because in your proof you say you assume Shokroff, if M is semi-ample, then so you regard this as kind of does not give trouble.
The usual divisor, yeah.
Yeah, so that's what my question. You assume M is semi-ample, so you have two different way. Anyway, that's my question. So the other question is that you have this effective version of frequency, given the frequency upstairs, say if it's epsilon LC, then you want to control downstairs. So your result is effective. Does it have a application, or instead of a theoretical bound, you have effective one? So does that give you application in other problems or something?
Yes, yeah. So that's a good question. So first, maybe I would like to make another remark that so the partial reason is that why we are all able to prove the relative dimension 1 case is that we need to apply the result of Prokop and Shokov, because in high dimension case the semi-ampleness of MZ is unknown, and so for the potential application of our results. So indeed, till now, I don't know any application. Yeah.
Okay. So thank you. So any other question from the audience?
So do you have any expectation for the case where relative dimension 2?
Yeah. So So maybe I add one more remark. So maybe one potential application is that maybe we are able to, but I'm not an expert in this area. Maybe we could classify the modifiable space in the case when X is canonical. So I think this is also an application of Iskof's conjecture, or when the case X is terminal. Yeah. So at least it is one of the motivations that's why Iskov proposed this conjecture. So they wish to classify the modifiable space. But I'm not the expert in this area. So about Professor Chen's question. So in dimension 2, so there's also some partial some results of Mori and Prokop. If I remember correctly, maybe about the Del Pezzo fibration, they showed that some value is about 1/6, but I'm not quite sure. Yeah. So under some assumption.
Abelian surface, is there any results on abelian surface? I mean, the fiber is. Is there any result? I think some similar results can be done on the abelian surface.
So I think this is very hard. You mean the fiber is some kind of abelian surface?
Yes, yes.
I don't know, because even in dimension 1 case, so if X is not of final type over Z, then in general you could not control the singularities of the pair. Because in a Calabi-Yau fiber, I mean when the general fiber is Calabi-Yau, then if you apply the Cordarius canonical bond formula, then you can see that in some case the coefficients will be very large, so 10 to 1. So this means that you could not control the base of the pair. And in higher dimensional case, I think it will be much more difficult.
Okay, so let's thank Jingjun for the talk. Thanks. Yeah. So the next talk will start at the scheduled time, 15 past 10. So 4 minutes break. Usually talk is 15 minutes. So 10 minutes for question. So maybe Jiajia can upload the PDF. Yeah. Okay. Thanks. Thanks, Jingjun. Yeah.
Thank you for your listening. Yeah, again.